So first off, they want us to write an equation for the line tangent to f at x equals 1. So to do that, right, for writing a tangent line equation, we need a point, which is the point 115, since they give us that. And we need a slope, which should just be 8. So we should just be able to write y minus 15 equals 8 times x minus 1. If you want to distribute or bring the 15 over, you're welcome to, but not required. And then it says approximate f of 1.4. So at 1.4 should be 8 times 0.4 plus the 15, which comes out to be 18.2. Any issues there with part A or questions on part A? That was really 2 points, 1 point for the approximation, the tangent line, and 1 point for the approximation. All right, part B, using a midpoint Riemann sum, 2 subintervals of equal length. We're going to approximate the integral from 1 to 1.4 of f prime, and then we're going to use that to estimate the value of 1.4. So let's first use that Riemann sum. So if we're doing a midpoint Riemann sum, we're going to take the midpoint from 1 to 1.2, which is at 1.1, and that's a height of 10. So we should just have 10 times the length of that interval, which is 0.2, plus, and then the midpoint of 1.2 or 1.4 is 1.3, so that's the value of 13. And again, times a 0.2, and that's what, 2.6 and 2, so that should be 4.6. So that was worth 1 point, getting that answer of 4.6. Then it wants us to use that value for that integral to estimate the value of f of 1.4. So we should be able to do that by saying that the integral from 1 to 1.4 of f prime of x dx, which is what we just found, should be equal to f of 1.4 minus f of 1. And so we got 4.6 for the integral. We're looking for f of 1.4, and f of 1 was 15. So it looks like this says it should be about 19.6. And that second part of that, part B there, was 1 point if you set this up correctly, and 1 point if you got the right answer. The 3 total points for part B. Any questions there on part B? Lots of good fun ways to approximate the value of f of 1.4, right? Part C, we're going to use Euler's method with 2 equal steps from 1 to 1.2 and then 1.2 to 1.4 to approximate 1.4. So first thing we'll need to do there is figure out what our slope is at 1. Our slope at 1 is 8, and we know that the step is 0.2. So if our slope is 8 and our step is 0.2, part C, we should be increasing our y value by 1.6. And so what was our original value was 15, right? So our first point was 1, 15, which then tells us that our next point should be 1.2, 16.6. And then we'll use our slope at 1.2, which is 12. So we'll do 12 times 0.2, because that's our step again. So that should be 2.4. And so we should go up to the point 1.4. And what does that come out to be? 19, it looks like. And so 19 is our approximation for f of 1.4. So that was worth 2 points, 1 for correctly using Euler's method and 1 for saying that f of 1.4 was 19. Good or no? And lastly, we'll use, I believe, it's a second degree Taylor polynomial about x equals 1 to approximate f of 1.4. So first off, we need the second degree Taylor polynomial, which should be starting with a 15, since f of 1 was 15. And then f prime of 1 was 8, so it should be plus 8 times x minus 1. And then the next one, f double prime, was what? They gave us 20 for that. So plus 20 times x minus 1 squared over 2 factorial, or just over 2. So then we're just going to approximate this at 1.4. So that'd be 15 plus 8 times 0.4 plus 10 times 0.4 squared. And that comes out to be, what's that, 18.2, 1 point. What does that come out to be? That's for some reason I can't do arithmetic today. 19.8. Does that sound right? Cool. And that one was worth 2 points. 1 for the polynomial, 1 for the answer of 19.8. Everybody good there? Any questions on that one? Did y'all get 9 out of 9 there? Excellent. All right. Part A should have been pretty straightforward, finding the average value of g on that closed interval. So that ought to just be 1 over 4 minus 1 times the integral from 1 to 4 of g of x. So 1 over, I'll even write it as x to the negative 1/2, just because looking at it that way makes the integration easier. We got 1/3 of 2 root x from 1 to 4. And so we end up with 1/3 of 2 times 2 minus 2 times 1, which should be 2/3. Everybody okay with that? Any questions there? One point for the correct integral, 1 point for the correct value at the end. Everyone good there with that? All right, part B says S is the solid generated when you take that region between g of x, x equals 1, x equals 4, and the x-axis, and take it around the x-axis and revolve it. So that should just be pi. And since that region is fully pushed up against the x-axis, it's just disks. So pi times the integral from 1 to 4 of the radius, which is just the function squared, and 1 over root x squared is 1 over x. So this should just be pi times the natural log of the absolute value of x from 1 to 4, or pi ln 4 minus pi ln 1, or just pi ln 4. Good or no? We got 1 point for the right setup and 1 point for correctly anti-differentiating and evaluating it. For part C, is talking about this same solid S. We want to find the average value of the areas of the cross sections that are perpendicular to the x-axis. Well, the cross sections that are perpendicular to the x-axis are just circles, right? I mean, it's just this same basic function here that we're really, I mean, the 1 over x times the pi just represents the area of that cross section. So if we're looking for the average value of that, it should just be 1/3, 1 over 4 minus 1, times the integral from 1 to 4 of pi of 1 over x dx again. And we already know what pi times 1 over x dx is. It's pi ln 4. So this should just become 1/3 pi ln 4. And that one was just worth 1 point. Any questions there on part C? All right, part D. Part D gives us a fun little thing here going on. We've got the average value of a function on an unbounded interval. So they've defined this now as the limit as b approaches infinity of the integral from a to b of f of x dx over b minus a, which is the same as a regular average value. So we want to first show that the improper integral from 4 to infinity of g of x is divergent, but that the average value of g on that interval is finite. Okay? So we're going to show that there is an infinite amount of area underneath that curve from 4 to infinity, but that the average value of the function actually does exist. So first off, we're going to do the integral from 4 to infinity of 1 over root x dx, which should then be written as the limit as, they were using b, so we'll use b here. The limit is b approaches infinity of the integral from 4 to b of 1 over root x, or x to the 1/2, negative 1/2 dx, which should be the limit as b approaches infinity of 2 root x from 4 to b, which then just becomes 2 root b minus 2 root 4 as b goes to infinity, which is infinity minus 4, which is still infinity, which shows that it's divergent. So for the first half of that, you got 1 point for showing that this comes out to be 2 root b minus 4. So 1 point for this, and 1 point for stating that that's divergent because it's infinite. And then for the second part of it, where it asks us to show this average value of it, should all be the same basic setup here. It should be the limit as b approaches infinity of, and then it's this integral from 4 to b of x to the negative 1/2 dx all over b minus 4. And while we already found the integral from 4 to b of x to the negative 1/2, right, that became 2 root b minus 4 over b minus 4. And if we let b approach infinity, what does this become? Should be 0, right, which is a finite value. So we've shown that this approaches, that this limit is 0. So the average value of the function 1 over root x from 4 to infinity is 0. Yet there is an infinite amount of area underneath it. And that's worth 1 point for the right setup and 1 point for getting your finite value at the end. All right, I'm waiting, Nick. Well, it's infinity over infinity, yes, but it's something that increases less rapidly over something that increases more rapidly, right? A root function will increase less quickly than a linear function will. So it comes out to be 0. Alternatively, I mean, you can take the derivatives if you want. If you take the derivatives of it, you'll end up with 2 times 1 over 2 root b over 1, which just is 1 over root b, which is then quite obviously 0. Yeah, you can do L'Hopital's rule. I mean, it's infinity over infinity for sure, but you don't necessarily need to use L'Hopital's for that one because that's just kind of a known fact that if you got a root over a linear, the linear increases more rapidly. All right, any other questions on that one? How do we feel about that one? Not too bad? All right. I don't think that we have enough time to give you guys time and to go over another one today, so that'll be the last one that we do together.